Okay, we're already 40 in the conference. So, good morning everyone. Kamusta po? This is our last meeting for this course. So, let's make it productive. So, yeah, let's begin. If we are ready to learn today, please type relative equilibrium in the chat box. Okay, thanks. Let us start. I'll share my screen. Okay. So, this is the last topic for this course under Module 6. So, we have relative equilibrium of liquids. So, to start, let us define what relative equilibrium of liquid is. So, when we say relative equilibrium, it's the condition where every particle of a liquid is at rest with respect to every other particle and to the containing vessel. Now that's uh, definition. That definition is quite vague, no? So let's have another. So when we say relative equilibrium, it's a condition okay. Pagpasensyahan niyo na lang yung pangit na sulat. So definition of relative equilibrium, it's a condition where the whole mass of liquid, including the vessel in which the liquid is contained, is moving at uniform accelerated motion with respect to the Earth. So, for example, we have a beaker. So, a beaker is a container. We can contain fluids in a beaker. So, let's say we have this water that's inside this beaker. Now, let's say this beaker is in static position. So when it is in static position, the water is in equilibrium. So it there is no change in the position of the water, right? So kung walang force na i-apply doon sa beaker, stationary lang siya. So of course, hindi siya gagalaw. Unless it's acted upon by a force, so saka siya magmo-move. Okay, so that's Newton's second law of motion, no? So this is the first case. The water in the beaker is just stationary. So we can say that it is in equilibrium. But say we apply a force in this beaker. So let's say that is case 2. So we apply a force. And this force is a horizontal force. Okay, so we applied it on this side of the beaker. So what will happen to the water? So the water will of course move. Okay, so we apply a force in this side of the beaker. So therefore the water will move. So there is a change in position. Okay, so we apply force. And what again is a force? It's either push or pull. And mathematically, we represent it as mass times acceleration. So basically, this beaker has a constant acceleration due to the force applied to it. Now, going back to case 1, wherein the acceleration is 0, the beaker is in equilibrium, or the water is in equilibrium. So there is no change in position. There is no translation. But in case 2, we apply a force. We push this beaker to the right, so it changes in position. So therefore, we have this uniform accelerated motion. Okay? Now, sir, what if we have a beaker that is in constant motion but with 0 acceleration? Then we can say that the water inside of that container is still in equilibrium, just like in case 1. Okay? So we can only say that the liquid is in relative equilibrium if it's in constant motion with acceleration. If it has zero acceleration, either it's stationary or it has a constant velocity, then it falls under this case 1, in which the water is in equilibrium. Now, sir, ano yung application nito sa fluid mechanics? We're considering na gumalaw si beaker because of a force. Okay, it contains it contains this constant acceleration because of this force. The pressure changes because here now we can see that the position of the water changed. So the pressure at this point is different at the pressure at this point. Okay, so it has different formula or different a way of solving compared to this case 1 that has no acceleration. And that's what we're gonna focus on today. No? So relative equilibrium for rectilinear vessels. So what do we mean by rectilinear? Rectilinear means the vessel is traveling in a straight line. Okay, so we have a motion. It's traveling in a straight line, either horizontally, vertically, or inclined. So those are 3 different cases. Okay, so let's talk about those 3 different cases. So delete ko po ito, no? Delete ko po ito. So let's start with vessel that is traveling in an inclined path. So we have this container or vessel that has wheels on it and it's traveling in this slope or inclined surface. So we have the angle of this inclined surface as alpha, and it is filled with water. So the position of water will become this, right? So it travels in this direction. So we have an acceleration towards the right. Now let's analyze the forces involved in this case, okay, wherein we have an inclined surface. Okay. So we have 3 forces involved in this case. So we have the normal force, which is initially in this position. This is the normal force, and then in-extend lang. Kaya napunta siya dito. And then we have the self-weight of the liquid. And then we have the R. Okay, what is this R? This is called the inertia force. Or reverse effective force. Okay, so we have these three forces involved in this scenario. Now we can put it in the x and y coordinate axis, and we can take the summation of forces. So this is theta, this is also theta, this is also theta, also theta. So we can reduce the inertia force into two components. It's a horizontal component and vertical component. So horizontal component is equal to mass times the horizontal component of the acceleration. Okay, because this inertia force equals ma, right? So R sub h is equal to m times a sub h. And then for the vertical component, R sub b is equal to mass times the vertical component of the acceleration. Now we can draw a right triangle out of this. So here we have the theta. And this is also theta. So right triangle using the tangent function. So tangent is opposite over adjacent. So we have R sub h. So that's the horizontal component. So opposite over adjacent. Now, saan nanggaling yung mg plus m times ab? So, yung vertical component natin or itong adjacent side ni right triangle is mg, okay, weight equals mg, and then R sub b. Now, they are both going down. Therefore, the sign convention is plus. Okay, we add the two. So, this is mg plus m times a sub b. Plus because they are both going down. Now, we can remove the mass because it's common to all of them. So, the final equation is this. Tangent theta is equal to the horizontal component of the acceleration over the gravitational acceleration plus or minus a sub v. Okay. So this is the equation to remember. Okay, if we encounter this problem, inclined relative equilibrium, inclined vessel, we can use this formula directly to solve for the unknown. Okay. So that's the first case. That's the first case. A vessel that is inclined, that's in motion. No? Now let's talk about a vessel that's traveling vertically. Okay, so this vessel is going up. Let's take a portion of the fluid. So it has a height. Now let's consider the weight of the fluid. It's equal to gamma times the volume, right? Also, it's equal to gamma times the height times the area. Now this will be counteracted by the force. So we have force equals pressure times area from the formula P equals F over A. And what is the last force? We have R, or the reverse effective force, which is equal to mass times acceleration. So given the weight, we can determine the mass by dividing it by the gravitational acceleration. Then we just multiply the acceleration of the vessel or the container. Okay, so with this, we can come up with the equation. So take the summation of forces along vertical equals 0. This is going up. It counteracts these two forces. So therefore, this is on this side, PDA equals the weight gamma HDA plus R. Again, weight is equal to gamma HDA. So we substitute this to this. And then we have over G times A. So we can cancel out dA and factor out gamma H. So we will have this equation. Okay. So to solve for the pressure of vessels that are traveling vertically, either up or down, we use this equation. Okay? So yung normal kasi is gamma H lang, no? So kapag stationary, si vessel. But if we have a vessel that's traveling vertically, so we use this. So let's solve some problems. Ah, okay. So let's have number 1. The barrel of oil rests on the surface of the scissors lift. Determine the maximum pressure developed in the oil if the lift is moving upward with a constant velocity of 4 meter per second, and letter B, a constant acceleration of 2 meter per second squared. Take the density of the oil to be 900 kilogram per cubic meter. The top of the barrel is open to the atmosphere. Okay, so we have a vessel that's going up with constant acceleration. So let me share my external cam. Let's solve this. Okay, let us have letter A first. It says that in letter A, the barrel has a constant velocity of 4 meter per second. Now going back to the formula that we derived earlier, we have P equals gamma H times 1 plus or minus A over G. So again, we use this if we have a constant acceleration. Okay? Meaning the pressure, no, will change if the vessel is either increasing or decreasing in terms of its velocity, because acceleration is change in velocity, right? Now, sabi sa question, sa letter A, constant yung velocity natin. Now, if we have a constant velocity, meaning the velocity is not increasing, not decreasing, ano yung acceleration? Equal to 0. So, again, we have a constant velocity, then we have no rate of change of velocity. So, acceleration is 0. Okay? So, if that's the case, this P can be still applied, right? Because we have gamma H times 1 plus minus 0 over G. So this will just be gamma H times 1 or gamma H. So solving for P, we are given the density. It's 900 kilogram per cubic meter. We multiply it by 9.81 meter per second squared to get the unit weight. and then we multiply the height of the barrel. So that is 1.25 meters. So this is the answer for letter A. Now let's have letter B. It says in this item, the barrel has a constant acceleration of 2 meter per second squared. So, we can now apply this derived formula. So, P equals gamma H times 1, either plus or minus. So, for the use of a sign convention, or use of operation rather, we base it on the direction of the vessel. So in number 1, we have a vessel that's going up. If it's going up, then we use positive or plus. If it's going down, then we use minus. So in this case, we use plus. So A over G. Solving for the pressure, if we have 2 meter per second squared na acceleration, that is 900 kilogram per cubic meter times G times the height, 1.25 meter, times 1 plus acceleration, 2 meter per second squared over G na 9.81 meter per second squared. So what is the pressure? Okay, 13.29 or 3 kPa or 13,286.25 pascals. Okay, so I'll accept both answer, either in Pascal or kilopascal. So that's how we solve problem number 1. Do you have any questions, Pop? Okay. So let's continue to, ayan, tanong si Mr. Patrick. Sir, saan po ulit nakuha yung 2 meter per second squared? Given po siya dito sa problem. So hindi lang nag-appear sa canvas sa BBB, pero ito po siya. Yan, a constant acceleration of 2 meter per second squared. Okay. Tas yung density ni oil, so ito din, hindi rin siya nag-appear sa BBB. So kaya sinulat natin. Ayan. So, so yun lang. If nakita tayo ng gantong problem na vessel na may lamang liquid. We can use this formula. Okay? Given na merong constant acceleration, no? So kung wala naman, constant yung velocity natin, meaning hindi nag-i-increase o nagde-decrease si velocity o kaya stationary si vessel, edi gawin lang natin 'tong 0. So ang magiging formula natin is gamma h. Okay. So let's have this last problem. Problem number 2. The truck carries an open container of water as shown. If it has a constant acceleration of, yan, wala na naman. So yung given na constant acceleration is 2 meter per second squared. If it has a constant acceleration of 2 meter per second squared, determine the angle of inclination of the surface of the water and the pressure at the bottom corners A and B. Also determine the maximum constant acceleration it can have without causing the water to spill out of the container. So, given tayo ng truck na nagmo-move siya to the right. So, going towards this direction. So, it has a constant acceleration, meaning bumibilis yung speed niya. Bumibilis at a rate of 2 meter per second squared. So, because of this increase of velocity or speed, there will be a movement of water inside of the vessel. So, magagalaw si water sa loob ng container. Kaya hindi siya magstay in equilibrium because of this 2 meter per second squared na acceleration. Now, ang kailangan nating malaman is yung angle of inclination. So, dito sa figure, ito siya. Okay, yan yung unang required. Tapos yung pressures daw at the bottom corners of A and B. So since may movement si water, magiging ganito yung position niya, ibig sabihin, hindi na siya magiging equal. No? Si pressure A at pressure B, tulad nung kanina na flat lang yung tubig sa surface. So, magkakaroon ng mas maraming tubig dito and dito mas magkakaroon ng konting tubig. So, mag-iiba yung pressure dito sa ilalim, point A, tsaka point B. And yun daw yung i-compute natin. Yun yung isa pang kailangan. And then, yung isa pang kailangan is ma-determine natin yung maximum constant acceleration it can have without causing the water to spill out of the container. So, hanapin natin acceleration na ganun yung case. So, para mas ma-imagine natin, i-drawing natin yan mamaya. Pero focus muna tayo sa pag-determine ng angle of inclination at yung pressure sa bottom corners of A and B. Now, para sa ganitong case, kasi I mentioned earlier that we have 3 cases, right? So, sulat ko muna, no? 3 cases. Una, inclined vessel. Pangalawa is vessel that travels vertically. And then pangatlo is vessel that travels horizontally. For the first two, inclined vessel and vessel that travels vertically, we already derived the equations. So for the inclined vessel, ito po yan. So para ma-determine natin yung angle of inclination, we have to divide the horizontal component of the acceleration by the sum or difference ng gravitational acceleration at vertical component ng acceleration. So that's how we can determine this angle of inclination for inclined vessels. And then for vessel that travels vertically, we can use this equation to determine the pressure. Gamma times H times quantity 1 plus or minus A over G. Now, we still haven't discussed the vessel that travels horizontally. Okay? So, given, let's discuss that, no? So, given that we have a vessel that is filled with water, and it travels in a horizontal flat surface. Okay? So we have an acceleration going towards this direction to the right. So let's analyze the forces involved in this third case. So because of this motion, because of this acceleration, the water will move. So from this position, from equilibrium, it will shift to this. Okay? So di ba kapag may baso ka, tapos nasa kotse, start mo yung kotse, magmo-move si baso or magmo-move si tubig, no? So ganun din dito. Magmo-move siya pag ganito, this way si tubig. So ano-ano yung mga forces involved? So forces involved, unang-una, si weight ni tubig. So weight always downward and it's equal to the mass times the gravitational acceleration of the Earth. And then ano pa yung ibang forces? Meron tayong normal force dito. And then we have the R, which is yan yung inertia force natin due to this movement. Now, based from this figure, we can draw its free body diagram. So we have a normal force here. We have a weight that's going downward. And we have the inertia force that's going towards the left. We have a right triangle. Now, where is theta? Where is the angle of inclination? So, angle of inclination, ito, saka ito. So, same lang siya. Now, if this is theta, in this figure, this is also theta. Okay? This is also theta. So, in the free body diagram, ito yung theta natin. Okay? So, to get this theta, we can use the tangent function. So, tangent is opposite over adjacent side. So, we have opposite R over adjacent side W. So, this R is equal to MA, and this W is equal to mg. We can cancel m. So, tangent theta for vessels that travel in a flat surface equal to A over G. That is the derived equation. Okay, so we can now solve for problem number 2. So drawing muna natin si vessel. So because of a 2 meter per second squared acceleration going to the right, it will move. Okay, the water will move. So, yung length ng vessel natin is 5 meters. So, mahati ito. This is 2.5. And this is also 2.5. So, ito yung theta natin na gusto nating malaman. Now, using the formula that we derived earlier, tangent theta equals A over G. So, we can substitute the given acceleration, 2 meter per second squared. And this is 9.81 meter per second squared. So, what is theta? Okay, 11.52 degrees. So, that's the angle of inclination. Now, next, we have to determine the pressure at the bottom corners A and B. So, how can we solve for the pressure? We can solve the pressure by multiplying the unit weight by the height. So going back to this figure, this is point A and this is point B. So we have to determine this height and this height. Now, if we know the angle of inclination and we have 2.5 meters here, this is a right triangle, we can use the tangent function to determine this delta H and delta H of point B and delta H of point A. Okay, so that's the change in the height at this point and this point. Para mas malinaw, drawing natin yung triangle. So from this, siya ngayon. So ito yung delta H sa B. And then ito yung 2.5 meters. Now ito yung gusto nating malaman. So tangent theta, opposite over adjacent. Theta is 11.52 degrees. This is multiplied by 2.5. So this is your delta H sub B. So what is delta H sub B? Sulat natin in 4 decimal places. 0.5095 meter. So sa delta H sub A, same lang din. Kasi 2.5 din yung adjacent side. Okay. We can now get the pressure. So pressure at point A is equal to 9,810 Newton per cubic meter times the height. So we have a height na 2 meters plus delta H sub A. So ilan po yung pressure in Pascal? Okay. Thanks, Andrea. 24,618.2 pascals. So what about pressure at B? Equal to 9,810 Newton per cubic meter times the height. So this height. Okay. So if this is 0.5095 meter and this is 2 meters, so para makuha to, it's 2 minus 0.5095. So, yan yung lalagay natin dito. 2 meter minus 0.5095 meter. What is pressure at point B? (14,621.8 pascals). .81. So, nasagutan na natin yung unang tatlong required ni problem. Angle of inclination, pressure at A and B. Now we have to determine the maximum constant acceleration the vessel can have without causing the water to spill out. So, kailangan natin siyang i-drawing for us to solve that acceleration. So, initially, the water is in equilibrium and then, sabi, maximum acceleration it can have without causing the water to spill. So, yung tubig natin, kailangan ma-reach niya yung highest point. No? So, this is 2 meters and this is 1 meter. So, kailangan ma-reach niya yung highest point ni vessel. Okay? And kailangan di siya dyan exceed. No? Because matatapon na yung tubig. So, kailangan malaman natin yung acceleration na magkakos ng ganitong motion sa tubig. Okay? So, going back to the derived equation, tangent theta equals A over G, we have to determine what is theta. Okay? So, hindi ito yung 11.52 degrees. Because yung height lang na maproproduce nitong angle na to is 0.5095. Okay? That's due to this 2 meter per second squared. So, kailangan natin malaman itong bagong theta na to. So, how can we determine that? So, if this is 1 meter, this is 2.5 meters, it makes a right triangle. So, this is 1, this is 2.5, and this is your theta. Using tangent again, so tangent theta is equal to opposite over adjacent. Ano yung angle natin? Okay, 21.8 degrees. Ito yung gagamitin natin dito. Okay? So, this is tangent 21.8 degrees equals A over 9.81 meter per second squared. Cross multiplying 9.81 to this side, what is the acceleration? So it's equal to 3.92 meter per second squared. So that's the acceleration that will cause the water to move in this position na hindi siya mag-i-spill. So yan yung maximum acceleration na hindi matatapon si tubig. No? So any other value higher than this, let's say for example 4 meter per second squared, matatapon na si tubig sa ganong acceleration, no? Sa ganong kabilis na increase ng velocity. So that's how we solve this problem. Any questions? Okay, so may tanong si Alexander. Sir, pag yung direction po ng horizontal acceleration baliktad, yung itsura rin po ba ng tubig pabaliktad? Yes po. So kung ganito yung direction, yung acceleration, so si tubig, magiging ganito naman. Okay. So any other questions? Okay, so we already published the PowerPoint presentation, and then we also published this discussion. So you have to answer this question. So in statics of rigid bodies, when we say that a body is in equilibrium, it means that the body is at rest with no motion. But on this topic, relative equilibrium, why do we say that the vessel is in equilibrium even though it is in motion? So that's the assignment for this module that you can answer until April 23. And then yung schedule po natin ng final exam is on Saturday from 10:30 AM up to 12:30 PM. Coverage from module 1 up to module 6. So I will give one problem per module. So please review all of the topics, no? All of the given problems, no? So ito lang din naman iikot yung ibibigay nating questions. Sir, pwede po hanggang gabi final exam. Hindi pwede Clarence eh. We have to have the exam na in our class hours. So I'm sorry. But if you cannot take the exam at that time, please send a valid excuse letter na lang, no, via Canvas inbox, and I'll open the exam whenever you're ready. Okay, I think ikaw yung nag-e-exam ng Sunday or Sabado ng gabi because of your religion. Yeah. I'll just open the exam for you na lang. Okay. So, any other questions po? Any other concern? If none, then you may leave the conference. Thank you for your attention today. I hope you learned something in this course, and good luck on your final exam. Hoping in the other courses magkita-kita ulit tayo.